Okay. Evening, everyone. My name is Chandan Kumar Gupta. I am a Prime Minister Research Fellow in Department of Mathematics, IIT Patna. I am your NPTEL TA for the course Probability and Statistics. This course is offered by Professor Somesh Kumar. He is a faculty in IIT Kharagpur. This is the 10th week of a 12-week course. Okay. Uh, in this week, we will mainly discuss about the confidence interval and some point estimation part also, like sufficiency and completeness. So we are discussing about statistical inference. Mainly statistical inferences stand for like conclusion. We will take some sample. On the basis of those collected sample, we will draw some conclusion. Okay, these are mainly categorized into two parts. The first one is estimation, and the second one is testing of hypothesis. Okay. Now, estimation is also divided into two subparts. The first one is like point estimation, and the second one is interval estimation. Okay. So in previous week, like ninth week, we have discussed about the point estimation. Okay. Uh, and in today's class, we will mainly discuss about confidence interval, which lies in interval estimation and some parts of point estimation. Okay. Like we have discussed about the good statistics have some properties. Okay. So statistics are the function of sample values actually. Statistics are the function of sample values, and these statistics is used to estimate the parameter. So that it is called estimator. Okay, and there are some properties we can say, like the first one is unbiasedness. The second one is consistency. Third one is efficiency. Fourth one is sufficiency. Okay, a estimator or a statistic have these four properties, suppose, then it is a good estimator. And that statistic or that estimator is called a good estimator. So like in previous, we have discussed about some, and today we will discuss about sufficiency. Okay, mainly so like sufficiency, like those sample is like a statistic is called sufficient. That means it contains all the information regarding the parameter or regard the amount of information that collected or included in the sample is contained in that statistics as well. So this is called the sufficient statistic. Like we can write in standard definition. Like suppose we have x1, x2, xn. These are the random samples from population. Then a statistic, suppose tx. It's said to be is sufficient if the conditional distribution, like if the conditional distribution of the whole, like x1, x2, xn, if the conditional distribution of this given this statistic tx is independent of theta or the parameter for almost all t in all statistics. Okay, then we say that the statistic or the estimator is sufficient estimator. Okay, so it is mainly data reduction technique. It is mainly, it is a like data reduction tool. Okay, like for example, suppose, suppose x follows Poisson lambda. Okay, then statistic t we have considered like x1, x2 up to xn, and size of random sample. In this case, e, which is summation of xi, it is a sufficient statistics. That means the information in this is equivalent to information is the summation of this. Okay, so this means here we are deal with n samples, n variables. Okay, and here it is only one variable, which is summation of xi. So it reduces the like data. Okay, it reduces the dimension of the data we are dealing with. So that's why it is a data reduction technique or data reduction tool. Okay. Okay, then there is a necessary and sufficient condition, which is a theorem, which is Neyman-Fisher factorization theorem, which is Neyman-Fisher factorization theorem. It states like suppose we have a PDF x1, x2 up to xn are the random samples we have taken from a PDF of distribution function. Then the joint PDF of those xi's, the joint PDF of those xi can be written as a product of two functions. The first one is like g theta tx, and the second one is like hx. Okay, so these two functions in which this is a function of theta and x, and this is a function of x only. So if we will able to write the joint PDF in this manner, then this tx is our sufficient statistics. Okay, so it is a necessary as well as sufficient condition for estimator to be a sufficient. Okay, and also like there is one remark like MLE. So MLE, if they exist, are the function of sufficient statistics. Okay, so MLE, if they exist, are the function of the sufficient statistics. Okay, and also one more point is completeness. These are some of the topic that is covered in the 10th week lectures. Okay. Completeness means like suppose X follows some distribution, okay, p theta, okay, and we may say that the family of distribution is said to be complete if expected value of expected value of the statistic gx is equal to 0 implies gx equal to 0, or equivalently we can say that probability that gx equal to 0 equal to 1 for all theta belongs to parameter space. Okay, so we say that it is a complete statistic. That means if the statistics, the expectation of the statistics is 0, that implies that statistic is also 0. Then this is a completeness property of a statistic or estimator. Okay. Okay, and then we will have a couple of theorems, like the first one is Rao-Blackwell theorem. Rao-Blackwell theorem is actually it used the sufficient statistics. Okay, let me write the first statement. Right, let dx be an unbiased. Suppose we have a statistic dx which is unbiased for g theta, and also like t be a sufficient statistics. Sufficient statistics, then ht, a new function which is defined as the expected value of this unbiased estimator given the sufficient statistic. This is unbiased for the theta, or the parameter, or the function of the parameter g theta, and it is mainly gives UMVUE. It is mainly used to give the minimum variance unbiased estimator. Okay. Also variance of HT is always less than or equal to variance of like TX. That means it always gives the minimum variance and it is unbiased. So that means it gives the minimum variance unbiased estimator. Okay. Now there is one more theorem, that is Lemon-Safet theorem. Okay. This theorem also suppose we have a statistic T which be a complete and sufficient. Then HT, suppose we have a statistic HT, it is said to be UMVUE for its expectation like g theta equal to expected value of this. Okay, so these two theorems are actually connected with each other, Rao-Blackwell, Lemon-Safet theorem. Okay, so these are the part of point estimation. Now we are going to discuss the interval estimation. Okay. Interval estimation, like it is also called confidence interval. We will also use the term confidence interval because there are probability terms are associated with these estimations. Okay, so that's why it is a confidence. There are some probability when we are dealing interval estimation. There are some probability associated. So that's why it is a confidence interval. Okay, so like similar. So confidence interval will be like suppose we have a x random variable and we have collected suppose x1, x2 up to xn random samples. Okay, we have a random sample. Then we will use two statistics in such a way. Suppose there will be two statistics. One is T1x and the second one is T2x. In such a way, like the probability of T1x, like g theta, it is a function of parameter actually, or maybe the parameter itself. T2x, this equal to 1 minus alpha for all theta belongs to the parameter space. Okay, so that means in interval estimation, we will use two statistics. And like we say, like we can interpret this. This can be interpreted like if we have n, suppose if we have n samples or n values, and we calculate this T1x and T2x, then this interval include 1 minus alpha percent times 1 minus alpha percent. Suppose alpha equal to 5%. That means 95% of the time, this interval include or contain this parameter theta or g theta. This is the interpretation of the confidence interval. Okay. Here alpha is the level of significance. And or 1 minus alpha, like if we are taking it 100, it is a confidence interval. Okay, or level of confidence. Okay, so in interval estimation we will use two statistics and the interpretation like this. Okay, so the next will be like now we will estimate and under different scenarios we will estimate the parameter in offer a confidence interval for the different sets of parameter. Like for example, suppose we will dealing with like confidence interval for normal with mu and sigma square. Okay, so again, first of all, we have like samples x1, x2 up to xn, which follows normal mu and sigma square. Is obvious. Then we will have two parameter mu and sigma. Okay, so like in first case, we want to confidence interval for mu. There are two possibilities. We need to calculate the confidence, construct the confidence interval for mu when sigma square is either known or unknown. Okay, so like suppose when sigma square known, sir has already like derived the formula. I am just directly write the formula. Okay, okay. So like no need to write the probability term. Like the overall, this can be mu can be estimated like x bar plus minus like z alpha by 2. Okay, and it's sigma by root n. It is because like here x1, x2, xi follows normal mu sigma square. This implies x bar. We already know that follows normal. That is mu and it is sigma square by n. Okay, so this is the expected value and this is the standard deviation. Okay, and this is the quantile, normal quantile, and z alpha by 2 is actually like this. Z is standard normal div. We can, okay. If xi follows this, then Z, which is equal to xi minus mu upon sigma, follows normal 0, 1. Okay, this follows normal 0, 1. That means this curve, we can write like draw like this. And suppose it is a point which is Z alpha by 2. For example, we have considered Z alpha by 2. So it is minus Z alpha by 2. We can take alpha 1, alpha 2 also, but for convenience purpose, we will take Z alpha by 2. So that means area under the standard normal curve is 1. And this is alpha by 2 area. And this is also alpha by 2 area. So this area is 1 minus alpha. Okay. This is the confidence. Okay. Now, if Pi for mu, if sigma square unknown, if we do not know the sigma square, then we will use the estimates, some other estimate of sigma square in place of sigma or sigma square. Okay, so in this case, like the confidence interval will be x bar minus plus like s upon root n, and here t alpha by 2 n minus 1 degree of freedom, because it is unknown, so 1 degree of freedom is less, so n minus 1 degree of freedom will be there. We have n samples and n minus 1 degree of freedom will be there, and s is the s, capital S square is 1 upon n minus 1 summation like xi minus x bar whole square, sample variance. S is sample variance actually. So we will take the minus sign and plus sign for lower and upper interval respectively. Okay, so these gives the interval estimates for mu when sigma square is either known or unknown. Okay, now the next will be like in a similar manner, like confidence interval for sigma square when mu is known or when mu is unknown. Okay, so there are all type of possibilities, and we will have questions on every topic. Okay, just for formula we will write like this. Okay, so sigma square is known and unknown in both cases. Okay, then first, because like in this case, it follows chi-square. Okay, like the class interval will be like this, not class, it's confidence interval. It will be like this. It's summation of xi minus mu, because mu is known, upon its chi-square alpha by 2 n, and the upper limit will be like xi minus mu whole square, and its chi-square, it's 1 minus alpha by 2 n. Okay, in the previous we have write like alpha by 2, t alpha by 2, here it is like z alpha by 2. Here we have written chi-square alpha by 2 and chi-square 1 minus alpha by 2, because it is chi-square distribution, or the curve for the chi-square distribution is not symmetrical. Okay, so like we may understand like this. Okay, slightly positively skewed, or in a similar manner. Okay, so suppose there are two terms. Okay, suppose we have take this like it is alpha 1, it is alpha 2. Okay, we will standardize this, so the area under this curve also becomes 1. So that means this is area alpha 1, this is area alpha 2, this is 1 minus alpha 1 minus alpha 2. Or for simplicity, for to like we will consider it's alpha by 2 and it is also alpha by 2. In this case, we will write like this. This point will be like it's like alpha by 2, and it's n degree of freedom. and in a similar way is 1, sorry, it is like 1 minus, it's 1 minus alpha by 2. Okay, and it's n degree of freedom. So these points are like this. Okay, and the area, it's alpha by 2, it's alpha by 2, it's 1 minus alpha. Both are similar thing actually. Okay, but for convenience purpose, we will write like this. Okay, so it is 1 minus alpha and alpha. And this value can be noted from the chi-square table under the degree of freedom and the level of significance. Okay. Now, suppose mu is, this is the case when mu is known. Mu is known. Like when mu is unknown. In this case, the Ci for sigma square will be like this: n minus 1 s square upon like chi square alpha by 2 n minus 1. It is n minus 1 s square upon like chi square 1 minus alpha by 2 n minus 1. Here, when it is known, the degree of freedom will be n. When it is unknown, 1 degree of freedom is also less. That means it is n minus 1 degree of freedom. Okay. Now the rest is, suppose we are dealing with the two population, two normal population like this. In this case, like suppose x follows normal, like xi or x follows normal, mu1 and sigma 1 is square, I from 1 to up to m, and yj follows like normal, mu1 it's mu2 and sigma 2 is square, j from like 1 to up to n. So in this case, suppose we want to construct the confidence interval for the difference of the mean. So in that case, we will write like this, like Ci for mu1 minus mu2. There are also many conditions when sigma 1 is square and sigma 2 is square are known, when sigma 1 is square and sigma 2 is square are unknown and equal, when they are unknown but unequal. So there are a lot of possibilities, and we have questions on all the topics. So like when it is known, for example, we can write like this, like when sigma 1 is square and sigma 2 is square are unknown, like are known, not unknown. Okay, in this case, we can write like this: x bar minus y bar, it's minus plus sigma 1 is square m, sigma 2 is square upon n alpha by 2. This gives the confidence interval for 1 minus alpha percent confidence interval. Okay, so this is the case. Similar manner, if it is unknown, unequal, it is unknown and unequal. So in a similar manner, we have different types of these formulas, and we will evaluate. Okay, so we will start with the questions from now. Okay, like suppose the first question will be like, let x1, x2 up to xn be a random sample from a population with PDF. Given PDF is fx theta equal to theta x to the power theta minus 1 for x lies between 0 to 1 and theta is greater than 0. Okay, we need to find the sufficient statistics for theta. Calculate the sufficient statistic for theta. Okay, So for sufficient statistics, we have like factorization theorem, which is necessary as well as sufficient. So using the same concept, okay, using the same concept, we will first find out the joint distribution. Then we will try to write those joint distribution in two different functions, out of which one is a function of parameter and statistics, and the second is only the function of x. Okay, so we are given the PDF is like this. So the joint PDF can be written like this: theta xi to the power theta minus 1. Now it can be written theta to the power n, and it's product of xi to the power theta minus 1. Okay, this can also be like written as theta to the power n, like we can write like this, like product of xi to the power theta minus 1. Now we can write like this, theta to the power n. These are simple, na? Theta to the power n. So product of xi to the power theta into 1 upon product of xi. Okay, minus 1 can be written down in denominator part. So from here we can see that this and this. So this is our g theta tx, and this is our hx. And here this tx is our sufficient statistics. So that means here like our tx, which is equal to product of xi, and hx equal to 1 upon product of xi. So tx is our sufficient statistic. So sufficient statistics is product of xi. Okay, with the help of Fisher-Neyman factorization theorem. Okay, only we will write the joint distribution and we will arrange in this manner. Okay. Now the next question will be like, next question is like, suppose we have let x1, x2 up to xn be a random sample from Bernoulli distribution. Okay, so that means our fx theta will be like this, theta to the power x, 1 minus theta power 1 minus x for x equal either 0 or, okay. Now we have some statements. The first statements will be like this, a statistic t which is equal to summation of xi I from 1 to 1 is complete statistic for theta. The second statement will be like this, xi is sufficient statistics for theta. And the third will be like t divided upon n, that is 1 by n summation of xi is umvue for theta. We have three conditions, like three statements. We need to check these three, either one is correct or the other or all. Okay, so for this purpose, our first question will be like, summation xi is complete statistics for theta. Okay, for completeness. Okay, so like there's completeness, there is sufficiency, and there is UMBU. Okay, first let's start with sufficiency. Okay, for sufficiency, again we will write like this: joint PDF of, sorry, not this, joint PDF, which is equal to like product of theta to the power x 1 minus theta 1 minus x. Okay, so this can be written like this: it's theta summation of xi, here it is xi. Okay, and it is 1 minus theta summation of 1 minus xi, that is n minus summation of xi. Okay. Okay, so it can also be simplified as like theta to the power summation xi and 1 minus theta whole to the power summation of xi and 1 minus theta to the power n. Okay, now it is a function of parameter theta. It is a function of parameter theta. So we will write like this: 1, which is a function of x. Hx equal to 1 actually. We will write like hx equal to 1. Okay, so from here we will, this can be the parameter, the function of the parameter as well as the statistics, and this is the function of x alone. Okay, x to the power 0, it is also function of x. Okay, so from here we will say that like here tx equal, or hx, not tx, I've written the word hx. Here hx equals summation of xi, which is our sufficient statistic. That means our second option is the correct one with the help of factorization theorem. Okay, now the first one is like for completeness. For completeness, we will have to write like suppose expected value of tx equal to 0 implies tx equal to 0. This is the definition for completeness. Okay, so we are given tx is complete. Okay, so expected value of this equal to this, and also here, let me write here, since x follows Bernoulli theta, this implies t, which is equal to summation of x. This follows binomial and theta. It is clear up to this point, the property of Bernoulli random variable. Okay, so this means that, okay, now the expected value of tx. So that means what? Probability that t equal to t, the PDF of, or the PMF of the Bernoulli binomial distribution will be like this: NCT theta to the power t 1 minus theta to the power n minus t. This is the PMF of the Bernoulli binomial distribution. Okay, now we need to calculate the expected value. Okay, now we need to calculate the expected value of tx. Okay, and here we have considered it, suppose htn, whatever we want. Suppose we will take hx. Okay, in this case, summation, because expectation of x is x into fx. So expectation of hx is hx into nct theta to the power t 1 minus theta to the power n minus t, like t from 0 to n. Okay, So from here we will merge these two. So we may write like this. Suppose h star x theta to the power t 1 minus theta to power n minus t. Okay, this should be 0. Okay, for completeness, this should be 0, implies this equal to 0. So this should be 0. Now here theta is a probability of success which is greater than 0. So that means it is not going to be 0. It may also not be going to be 0. From here, from this statement, we may write like this equal to 0. And h star x is nothing. From here it is because NCT is also positive. So that means hx equal to 0. So that means our like the statistics Tx which is equal to summation of xi I from 1 to n is complete as well. Okay, because it is only possible to be 0 if this hx is equal to 0, then the expected value of hx equal to 0. That means hx is a complete statistic or tx is a complete statistic. Okay, and the third one will be like t by n, which is 1 by n summation xi. It is a UMV UE. Okay, now for UMV UE, we will use the Lemon-Chaffee theorem. Okay, now like using Lemon-Chaffee theorem, like we may say that if T is complete and T is sufficient, then HT is UMV UE for its expected value. Okay, so it is simple. So T is sufficient and T is complete. We have already proved those things. So that means we need to find nothing but like g theta equal to like expected value of ht. It's not tau, it's t. Okay, this is statistics. This gives our UMV UE. This ht is UMV UE. So here ht equal to what? We are given ht equal to t by n. And t by n, that is this. So expected value of ht, that is expected value of 1 by n summation of xi. Okay, so now it is like 1 by n summation of expectation of xi. We will write like this. Okay, and xi follows Bernoulli. It is already given here. Xi follows Bernoulli distribution. So the expectation of xi is theta. Okay, so that means it is 1 by n into theta. This gives out to be theta. So with the help of Lemon-Chaffee theorem, we may say that P by n, which is equal to 1 by n summation xi is UMV UE. Okay, am I audible? No? Can anyone confirm I'm audible or not?
Yes, sir.
Okay, thank you. Okay, so now the next question. That means what? That means all the three statements are correct actually. Okay. So the next question will be like, suppose let we have x1, x2 up to xn be a random sample from the PDF fx theta, which is defined like this: 1 by theta e to the power minus x by theta for x lie within 0 to infinity, that is x is greater than 0. Okay, now we need to calculate the Kramer-Rao lower bound for variance of an unbiased estimator of theta. Okay, so find Kramer-Rao lower bound, CRLB in short, for variance of unbiased estimator of theta. Okay, suppose we have an unbiased estimator and we need to calculate or found the bounds, that is inequality. There will be a bound method, there is an inequality. Okay, for the variance, or the variance of that estimator. Okay, so CRLB actually is Kramer-Rao like inequality. It is like defined as, suppose T is an statistic or an estimator, then variance of T is either greater than or equal to the parameter, the first order derivative of the parameter whole square and divided upon expected value of del theta of log of L its whole square, the expected value of the whole square of the first order partial derivative of log L. Okay, or this can also be equal to like minus times of expected value of second order partial derivative of log L. Okay, whichever is easy to calculate, we may follow that. Okay, so this gives the minimum variance of that unbiased estimate. Okay, this is the Kramer-Rao lower bound. So we need to calculate for theta. So like first we need to write the likelihood L, which is equal to product of fx theta, and fx is 1 by theta. Okay, let me write. It's not theta, it's n. It's 1 by theta e to the power minus by theta. Okay, so we may write like this: theta to the power n e to the power minus of summation xi upon theta. Okay, now we will take the log because we need to log L. So log L equal to minus n of log of theta and minus of summation of xi upon theta. Okay, so log L will be written like this. Now we will differentiate it partially. So del theta of log L will be like minus n upon theta. It's minus minus plus summation of xi upon theta square. We may use the second derivative also, del 2 log L upon del theta 2, which is equal to, it's minus minus plus n upon theta square, and it is minus summation xi upon theta cube and then multiplied by not 3, it's 2. Okay, so this is our this value. Okay, and we need to calculate the CRLB for theta only. So that means it's like the first order is, so expected value of del 2 upon del theta 2 log, sorry, log L equal to will be like expected value n upon theta square minus twice upon theta cube summation xi. From here it is n upon theta square is constant, so expected value of this is also n upon theta square minus 2 upon theta cube summation xi. Okay, summation xi, again xi follows our, this is actually exponential distribution, if you can able to guess. So it is exponential distribution. So the it from here the mean value is, or expected value is theta. So that means n times of theta, n times of theta, because summation of expectation of xi, this gives n into expectation of xi, which is equal to theta. So from here it is n upon theta square minus 2n upon theta square, and after solving it is minus n upon theta square, and we are given gamma theta equal to theta here. This implies gamma theta dash is actually 1. So our CRLB will be like this. It is gamma dash theta whole square and divided by minus of expected value of del 2 log del theta 2, which is equal to 1, and whole divided upon minus n upon theta square, and it's minus, which comes out to be theta square by n. So this is our answer. This is the minimum value of variance for theta, for the estimator. Okay. Now the next question will be like, suppose like we have x1, x2 up to xn random sample of size 11. Okay. Let x1, x2 up to x11 be the random sample from normal population with mean mu, and variance will be like 9.9. Okay. And if summation of xi, I from 1 to 11 is given as like 132, we need to calculate the CI, 95% CI for mu. So construct 95% confidence interval for mu. Okay. Here, since sigma square is known, okay, so in this case, like since sigma square is known, so that means our confidence interval will be this sigma by root n z alpha by 2. Okay. So now x bar, the first one is, what is x bar? X bar is 1 by n summation of xi. Here n is 11, so 1 upon 11 into summation xi is 132. So it is 12. Okay. Now Okay. Sigma upon root n equals root of 9.9 root of 11, which is equal to 9.9 on 11. This comes out to be like 0.9 under root of 0.9, which is approximately equal to 0.9487 and something, or we can say that directly it is 0.95. Okay, so we have to find the 95% confidence interval. It is asked in the question. So, okay, Z alpha by 2. Okay, so Z 0.025 is the value of this, which is actually Z alpha by 2. It is 1.96, like using normal distribution table. We directly use online calculator also. Okay, so we have all the values actually now. So our CI will be x bar minus plus of sigma by root n z alpha by 2, which is equal to like 12. It's minus plus. This value will be like 0.95 into 1.96. Okay. From here it will be like 12 minus plus, and this value will be approximately like 1.862. So our confidence interval will be this minus 1.862 and 12 plus 1.862. So our final CI will be like 10 point, it's 138, and it's 13.862. So like 95% of the time, okay, this estimate lies with the parameters lie within these two estimates, 10.138 to 13.862 for these given data. Okay, so this is the confidence interval. Okay, now next question will be like a random sample of 9 observations. Random sample of 9 observations from normal population yields the observed statistic x bar equal to x bar equal to 5 and 1 by 8 summation I from 1 to 9 xi minus x bar whole square equal to 36. Okay. Now we need to construct the 95% confidence interval for mu. Construct 95% confidence interval for, here it is clearly the variance is not known. We need to calculate the confidence interval for mu when sigma square is unknown. Okay, so EI for mu when sigma square is unknown. Okay. Ci for mu, then sigma square is unknown, is x bar minus plus of, when it is unknown, it gives t distribution. It's sample variance under root of like n and p alpha by 2, and degree of freedom is n minus 1. So the first is like x bar, which is already given 5. S, we need to find S. Okay. So as we know that S square is equal to 1 upon n minus 1. Summation over xi minus x bar whole square. Okay. This is now we can write like 1 upon 9 minus 1. Summation over xi minus x whole square. Okay. And this value is actually equal to 36. It is given. This is 36. So from here, like S square is equal to 36. This implies S is under root of 6. Sorry. Under root of 36, which is equal to 6. Which is equal to 6. Okay. So we have root, n value is, there is 9. And we have now t at alpha by 2 and n minus 1. So t value at 0.025, because it's 95% confidence interval, that is alpha equal to 0.05. So alpha by 2 is 0.025 and n equal to 9. So degree of freedom will be n minus 1, that is 8. Okay. So the value for this is, when using the t table, we will find out 2.306. Okay. So this is our values. Now the Ci will be bar minus plus of 6 upon root 9 into 2.306. Okay. So from here, it will be like 5, it's 6 upon 3 into 2.306, which is equal to 5 plus minus 2 into 2.306, that is 5 plus minus of 4.612. Okay. Now the Ci will be 5 minus 4.612 and 5 plus 4.612. This gives like 0.388, I think. Yes, 0.388, and the upper limit will be like 9.612. So this is our confidence interval for mu when sigma square is unknown. Okay. Now the next question will be, let x1, x2 up to xn be a random sample of size 13 from a normal distribution. Okay. So we have like x1, x2 up to xn, are normal sample, normal from normal distribution, random sample from normal distribution with mean mu and variance sigma square. Now, if actually here n equal to 13 is given. Okay, like if summation I from 1 to 13 xi equal to 246.61, it is given. Also, Also summation over I from 1 to 13. It's summation xi square is also given 4806.61. Then we need to find the 90% confidence interval for sigma square. Okay, here mu is not known. Okay, and we need to construct the CI for sigma square. Okay, so CI for sigma square when mu is unknown. Okay, so in this case, we know the formula for CI. CI will be like n minus 1 s square upon like chi square alpha by 2 it's n minus 1 n minus 1 s square chi square 1 minus alpha by 2 n minus 1. So this is our uh, the two statistics. Okay, for confidence interval. So the first one is like what is x bar because we need to calculate s square. Okay, so x bar will be like 1 by n summation of xi, which is equal to 1 upon 30. Summation of xi will be like 246.61, which is 18.97. Okay, summation of xi will be like this 18.97. Okay, now s square. S square will be like 1 upon n minus 1 summation over xi minus x bar whole square. And we may know that like if we expand it, a minus b whole square, that is a square plus 2ab plus b square. Sorry, a square minus 2ab plus b square actually. Okay, so that is what? That is it's xi square minus x bar square plus x bar square minus of twice x bar xi. We will apply summation. Okay, so it will become like this summation over xi square plus summation over x bar square. So it is n times, no? Clearly. It's clearly like n times of x bar square minus of 2x bar square summation over xi. And just after simplification, we may write like this. Okay, we will apply summation over this. It becomes nx bar, then nx bar square to nx bar square minus of nx bar square. So overall, it can be written like this summation over xi square minus of nx bar square. Okay, so now we have these quantity actually 1 upon n minus 1 equal to 13 minus 1, 12. Summation xi square is given here 4806.61. So it is like 4806.61 minus of 13 and x bar will be like 18.97 whole square. Now we may write like this 12 of s square equal to 12 of s square will be equal to like 4806.61 minus of 4678.19. And after calculation, we will find out 12, sorry, 12 of s square will be like 128.42. Okay, so we have n minus n equal to 13 here actually. So n minus 1 s square, which is in the numerator part. N minus 1 s square, n equal to 13. So 12 s square will be like this. Okay, so we have now chi square at alpha by 2 and this. Okay, so that means now chi square alpha by 2 and 1 minus alpha by 2. So like chi square alpha by 2 at n minus 1 degree of freedom, or like alpha is also given. Alpha is like 95%, so it is 0.05. Okay, it is given here 90% confidence interval, so 5% will be there. So 0.05. Okay, so the value, this value will be taken from the chi-square table under degree of 12 degree of freedom, and we will find out like this 5.23, and chi-square 1 minus 0.05, that is 0.95, and it is 21.03. Okay, so we have all the values now. Now the CI will be like 12 s square upon chi-square 0.0512, 12 s square upon chi-square 0.95 and 12, which is equal to 12 s square will be 128.42, and it's divided by chi-square 0.05, which is equal to, okay, I think it's actually it is 21.03 and it is 5.23. Okay, so that is, it is 21.03 and 28.42 equal to it's 5.23, and after solution we will get, it is approximately 6.11 and it is 24.55. So this is the confidence interval for 90%. Okay. Now the next question is, in a sampling from a distribution with variance of 25, how large must the sample size be so that the length of a 95% confidence interval for the mean is 1.96? Okay, so let me write the question first. In a sampling from a distribution with a variance of 25, how large must the sample size be so that the length of a 95% confidence interval for the mean is 1.96. Okay, so that means we are given the variance. Okay, that is, it is known, And the CI for the mean is then CI for the mean when variance is known is x bar plus minus sigma upon root n z alpha by 2. Okay. So here alpha by 2, z alpha by 2 for 95% is like this. For 0.05, that is 95% confidence interval, it is like 1.96. Sigma will be like 5. X bar will be like, okay, we do not have X bar as well. It doesn't matter because we want to, we are given like the length of the interval. Okay. So that means length equal to upper limit minus of lower limit, and length is 1.96. It is given the length is 1.96. It is equal to x bar upper limit plus z alpha by 2 is also 1.96. Please don't confuse. Z alpha by 2 value is 1.96 and the interval length, the length between the upper and lower limit is also 1.96 here. So it is the Z alpha by 2 value. Okay. And then sigma value is 5 by root n. We need to calculate n minus the same lower limit will be like x bar minus of 1.96 into 5 upon root n. Okay. So x bar will be cancelled out actually, and it becomes twice into 1.96 into 5 divided by root n, which is equal to 1.96. So 1.96 will also be cancelled out. So from here, like root n equal to 2 into 5, which is equal to 10. From here, n equal to 100. Okay. Is it clear now? We are just using this formula and the given data. Okay. Like the next question will be like, a random sample of 9 observation from a normal population with mu equal to 5 is the observed statistics, and what is, we need to calculate the CI for sigma square. Okay, let me write the question first. A random sample of 9 observation from normal population with mean equal to 5 and sigma square. Sigma square is unknown actually here. Okay, and we need to calculate the CI for sigma square. Okay. Also we are given like 1 by 8 summation of xi square I from 1 to 9, because there are 9 observation. It is 39.125, and summation of xi I from 1 to 9, it is 45. Okay, construct 95% CI for sigma square. Okay. So again, in this case, the CI will be like summation over, because mu is known here, na? So it is summation over chi minus mu square upon chi square alpha by 2n. If mu is unknown, then it is n minus 1 degree of freedom. It is known, so it is chi square alpha by 2 n degree of freedom, and summation over xi minus mu whole square divided upon chi square. It's 1 minus alpha by 2 n. Okay, so we have these values we need to calculate. So we have been, okay, mu is 5 already given, and summation xi square is given, summation xi whole square is given. Okay, so first, like summation xi, not square, summation xi is given, it's 45, okay, and 1 by 8 summation xi square equal to 39.125. This implies summation of xi square equal to 8 into this, which comes out to be 330. Okay, it is because we need to calculate this quantity, the numerator quantity. Okay, so now the numerator value will be like this: xi minus mu whole square, which is equal to, again, xi square plus mu square minus 2 mu xi. Okay, now this can be written as, we will summation over xi square plus n times of mu square minus 2 mu summation over xi. We have summation xi square, which is equal to 313 plus n is equal to like 9, and mu square equal to 25 minus 2 into mu into summation xi 45. Okay, so these are simple calculation. 313 plus, it's 275 minus 10 450, and after solution we will get like summation over xi minus mu whole square will be 88. Okay, it comes out to be 88. Now again we need to calculate 95% confidence interval. So chi square, it's alpha by 2, like 0.025, and n, which is equal to 9. The value of this is 19.02, and chi-square 0.975, because 1 minus alpha by 2 is this, and 9 degree of freedom is, it's 2.7. These two will be easily like seen from the table. Okay, so we have this value, we have these value. The numerator and denominator both value will be calculated. Now the CI will be 88 upon 19.2, 19.02, and it is 88 upon 2.7. And after solving, we will get, it is 4.63, and it is 32.59. Okay, so this is the confidence interval or sigma square when mu is known. Okay, now the next question is like, okay, we are given like in a survey of 40 small, in a survey of 40 small town coffee shop, and 49 big city coffee shops. we find that the mean price of a cup of coffee in a small town is $3.75 and in big city it is $4.50. Okay, now the population standard deviation in small town is 1.2 and in big city is 0.98. Okay, these are the data given. Okay, now we need to construct the 99% confidence interval for the difference of means. Okay, so we are given to a small town coffee shop and a big city coffee shop, and the respective mean and standard deviations are given. We need to calculate the 99% confidence interval for the difference of means. Okay, so like from this question, like we are given, like suppose n1 is a suppose small town coffee shop and n2 is a big city. So n1 equal to 40 is given and n2 equal to 49 is given. Okay, also x bar equal to like the mean price, it is $3.75 and it is like $4.5. Okay, and the population standard deviation sigma 1 is like 1.20 and sigma 2 will be like 0.98. Sorry, not 98, it's 0.97. Okay, I think in the question it is a 98. I have written it 97. Okay, so we are given this, and like 1 minus alpha percent is 99. Okay, this implies like alpha by 2 will be like 0.005. So Z alpha by 2 will be like 2.58. It is seen from, it can be seen from normal table. Okay. Now we have all the things. Now we need to calculate the CI for mu1 minus mu2. Okay. So again, for it is two, like there are difference of means. So the CI, the general form is like x1 bar minus x2 bar minus plus z alpha by 2. It will be like sigma 1 is square upon n1, sigma 2 is square upon n2. Okay, so this is the CI. Now x1 bar will be like 3.75, 4.50. It is 3.75 minus 4.50. Okay, minus z alpha by 2. The value of this is like 2.58, and it is 1.2 square divided by n1, that is 40 plus it is like N2 is sigma to 0.98 divided upon 49. Okay, so it can will be like it is minus 0.75 minus plus of 2.58 into under root of 0.0556. After solving, it gives this. Now again, it is minus 0.75 minus plus of 2.58 multiplied by its 0.236. Okay, and it is minus 0.75 minus plus of, and this is like 0.61. So the CI will be like minus 0.75 minus 0.61 minus 0.75 plus 0.61, and it comes out to be minus minus, it's minus 1.36, and it is minus of 0.14. So for difference of mean, the confidence interval, the 99% confidence interval will be like, okay, like okay, in a similar manner, if anyone have any doubt, he or she may ask, okay, because it is totally depend on the formula. We are given the data in our question, we use the formula and solve the or construct the CI. Okay. In case any doubt, please ask. Now the question number 10 will be like two local walk-in medical clinics. Okay. Two local walk-in medical clinic wants to determine if wants to determine if there is any variability, there is any variability in the time, in the time patient wants to see a doctor, in the time patients wants to see a doctor at each clinic. Okay, now the question is like in a sample of 30 patients at clinic 1, in a sample of 30 patients in clinic 1, the SD for the waiting time to see a doctor was 45 minutes. In clinic 1, 30 patients are observed and the waiting time will be 45 minutes. Okay. Now, in a sample of 40 patients from, in a sample of like 40 patients from clinic 2, okay, the waiting time will be like the waiting time be 20 7 minutes. Okay. Now assume the population of waiting time at the two clinics are independent and normally distributed. Okay, these are given like the waiting time is like independent and normally distributed. Normally distributed. Now construct the 95% CI for the ratio of the variance for the waiting time at the two clinics. Okay, we need to calculate the CI 95% confidence interval for the ratio of the variance of the waiting time for the two clinics. Okay, question is quite large actually, but is based on the ratio. So that's I have written. Okay, now the solution part will be, since we are given like there is clinic 1 and clinic 2, the number of patients for clinic 1 is 30 and for clinic 2 is 40, and the standard deviation, suppose S1 is square, it is 45 square, it is S2 square, sample variance will be 27 square. So it can be like 4, 5, 20, 25. 27 it is 729. Okay. Now mu1 and mu2 are unknowns. Okay. Here it is not given. So the CI for sigma 1 square and sigma 2 square is CI for sigma 1 square upon sigma 2 square is like this. It's S1 square upon S2 square. F, it is F table. We use F table for this. 1 minus alpha by 2. It is and 2 minus 1 and 1 minus 1. For F distribution, there will be two, a pair. The degree of freedom for F will be in a pair form. So n2 minus 1 and 1 minus 1 in this case. Okay, this, and the second one is S1 square upon S2 square F of alpha by 2 and 2 minus 1 and 1 minus 1. This is the form of the CI or the ratio of variance. Okay. So here alpha is 95%. So alpha by 2 will be like 0.05, 0.025. So that means F value at 0.025, its N2 is 40 and N1 is 30. That means it's 39 and 29. And this value is seen from like F table, and it is found to be 0.5097. Okay, and similarly F value for 0.975, 39, 29 will be like, actually this will be like 0.5097, and this is actually 2.032. Okay, so we have the F values. Now S1 square and S2 square is also given. So just to calculate, so CI will be like S2 square, sorry, S1 square, it's 2025 upon 729 into 0.5097. Again, 2025, 729, it's 2.032. 0.032. Only the calculation part is there. 2.78 multiplied by 0.5097. 2.78 multiply 2.032. Now it is approximately 1.417 and it comes out to be 5.649 after calculation. So this is the class interval, 95% confidence, 95% confidence interval for the ratio of sigma 1 square and sigma 2 square. Okay. Now the next question is like the next question we are given like consider x1 bar equal to minus of 1.6, x2 bar equal to minus of 16.3, s1 square equal to 8.9, s2 square is equal to 7.9, n1 equal to 23, n2 equal to 50. Now we need to construct a 95% confidence interval for the difference between the population means. Okay. So construct 95% confidence interval for a difference between the population mean. Assume when we assume the population variance are unknown and equal. Population variance are unknown, but it is equal. Then in this scenario, we need to calculate this. Okay. So in this scenario, like the CI for this is the formula for CI is like x1 bar minus x2 bar minus plus of n1 plus n2 upon n1 n2 the root and then pooled sample variance which is equal to SP, then it's T because we are dealing with the mean, which is T distribution. The T table is used here, alpha by 2, and the degree of freedom will be like n1 plus n2 minus of 2. Okay, because it is unknown, so n1 minus 1 plus n2 minus 1, that is n1 plus n2 minus 2. So this is the case here, where like SP square will be defined like this, like n1 minus 1 s1 square plus n2 minus 1 s2 square upon n1 plus n2 minus 2. It is a kind of combine, if you see, like combined sample variance, but it is called pooled variance. Okay, pooled sample variance. The formula is like this. Now our first aim is to calculate this, which is equal to n1 minus 1, that is 23 minus 1, 23 into s1 square is around 8.9 plus n2 minus 1, that is 15 minus 1, 14, s2 square, that is 7.9, n1 plus n2 minus 2, that is 23 plus 15 minus 2. So it is solved. Like the first one is like 195.8 plus the second will be like 110.6. The denominator will be like 36. After solving, we will get SP square is equal to 8.5 volt. This means SP equal to, because we need to use SP here, it is 2.92 approximate value. Okay, now SP will be calculated. N1, N2, X1 bar, X2 bar is already given. T alpha by 2, N1 plus N2 minus 2 degree of freedom will be uh, seen from like table, and this value will be T, it's like 0.025. So N1 plus N2 minus 2, it's like 36, and this value will be 2.0281. Okay, so the CI will be uh, x1 bar minus x2 bar, that is minus 1.6 minus of minus 16.3 minus plus under root n1 plus n2 divided n1 into n2. SP value will be like 2.92, and the last value T value will be 2.0281. It's all calculation only. Okay, so after simplifying this term, it will be like 14.7, and it is minus plus of this value will be like 0.332 into like 2.92 into 2.0281. Now it is 14.7, it's minus plus, it is 1.97. So our CI will be 14.7 minus 1.97, 14.7 plus 1.97. So this comes out to be like 12.73, and it's 16.67. So this is our like confidence interval for difference of population mean. Okay. Now there is some more questions. Let me complete it. Okay. The question is like, two methods were used to measure the brightness of independent clay samples. Two methods are used to measure the brightness of independent clay samples. Okay, the following table display the summary statistics for the two independent samples. Following data is given like method A and method B. Okay, so X bar will be 91.6, and S1 will be 2.3, N1 will be 12. Y bar will be like 92.5, S2 will be 1.6, N2 will be 12. Okay. Now we are interested in the difference between two population mean for the two methods. Now assume that the brightness measurements are normally distributed. Also assume that the population variance are unequal. Okay. So it is given. Like let me write the complete question. So we need to calculate the difference. Okay. like we are interested in the difference between the two population means for the two methods. Assume assume the measurements are normally distributed. Also, the we need to construct the 90% CI. Construct the 90% confidence interval for difference of means when variance are unequal. When variances are unequal. Okay, so this is our question. Okay. So for unequal variances, the CI for difference of mean will be CI for mu1 minus mu2 when variances are unequal is like this, is like x bar minus y bar minus plus t alpha by 2. Okay, t alpha by 2 into v, and then our it is s1 square plus upon n1 s2 square upon n2, because sigma square is unknown, so we use the statistics or some estimator of sigma square, which is s1 square. Okay, now we are given the means, the variances are unequal, so the degree of freedom here will be like nu, and nu will be calculated where nu will be calculated. Okay, sorry, it is calculated like this: s1 square upon n1 plus s2 square upon n2 whole divided by s1 square to the whole square upon its n1 square n1 minus 1 plus s2 square whole square its n2 square n2 minus 1. Okay, and this value up to the to the nearest integer, because we are going to evaluate the degree of freedom here. Degree of freedom will be integral value, nearest integer. Okay. So this will be solved with the help of the given data, which is already given above. Only we need to put the values and solve. So it is it's 2.3 whole square upon 12 plus 1.6 whole square upon 12 whole divided 2.3 whole square divided upon 12 square 12 minus 1 plus 1.6 whole square divided by 12 square 12 minus 1, and after solving it is a simple, actually we may solve with the help of calculator. It is around 19.3 377, which is nearest to the 19 as a integral value. Okay, so that means our degree of freedom will be 19. And alpha, since we need to construct the 90% confidence interval, so that means alpha equal to like 0.10, alpha by 2 will be like 0.05. So T 0.05 at 19. This value is seen from the like T table, and it is 1.729. Okay, and the rest value is already given. Now the CI will be like 91.6 minus 92.5, x bar minus y bar, minus plus of 1.729, and the value will be like 2.3 square upon 12 plus 1.6 square upon 12. Okay, only we need to solve it is minus of 0.9 minus plus of 1.729, and the bracket value will be solved like, and it comes out to be 0.8, and then the minus 0.9 minus plus of this value is approximately 1.40, and then the CI will be minus 0.9 minus of 1.40 minus 0.9 plus of 1.40, and it comes out to be minus of 2.3 and plus of 0.5. So this is the value when the when the variances are unequal and unknown, and this is the confidence interval for difference of population means. Okay. Now the next question is also there. Okay. The question is like let x1, x2 up to xn be a random sample of size n from normal with mean mu and variance 4 square, that is 16. Okay. If a 95% confidence interval for mu is like x bar minus 0.98, x bar plus 0.98. It is the 95% confidence interval for mu when sigma square is known, because sigma square is 16. Then what is the value of m? Need to calculate the value of m. Okay. So again, it is simple, since sigma square is known. So that means Ci for mu when sigma square is known is x bar. It's minus plus z alpha by 2. It's not sigma by root n. Simple. Okay. And the value is given because z alpha it's 95%. That means z alpha by 2 is, that is 0.025. It is 1.96. Okay. So our Ci will be x bar minus 1.96 into sigma is 4 upon root n. Again x bar plus 0.96 into 4 upon root n. Okay. Now we need to equate this with this. Okay. So equating or comparing this quantity with this quantity, we will get what? Like, sorry, 0.98 equal to like 1.96 into 4 upon root n. If you know this is the twice of this, so root n equal to like 1 point, okay, 1.96 into 4 upon 0.98, which comes out to be 8. So from here n equal to 8 square, which is equal to 64. Okay, so these are the type of question. We have I have also some question again, like but these are like similar questions, like we are given two samples of size 16 and 10 are drawn at random from two normal population, and the standard deviations are to be 25.2 and 20. We need to construct the 98% confidence interval for the ratio of the population standard deviation. Okay, and the similar type of question is there. Only we need to find out the which what is the formula we are going to use to construct the confidence interval. All the data or all the details are already given in the question. Okay, so this is it actually. If anyone have any question, please ask. Okay, so if not, we will conclude here. Anyone?
No, sir.
Okay. So then let me stop the recording.